Explain why CHCl3 Cl4 is not. Okay, so explain why CHCl3 is polar and CCl4 is not. Why? Okay, so for this one exactly, we actually have to draw our Lewis dot diagrams for both to explain it. So let's head over now to the periodic table. Sorry about that. I have a little sniffles. So carbon is on the 14th column, or exactly if we drew it out using our electron configuration, just to be able to practice that, you will see why it has 4 valence electrons. So we have, starting with helium for the shorthand, 2s2, 2p2. That is how this has 4 valence electrons. Hydrogen, as we discussed, is still just 1s1, hence why it's 1 valence electron. And chlorine, okay, is going to be, starting at neon for the shorthand, 3s2, 3p5, because we've already covered the s rows from the first and second column, okay, and then we have now from the 13th to the 17th column p5, okay. So that's how it's 7 valence electrons. So now, with that being said, okay, let me just quickly clear my nose. It's worse. Okay, and we're back. Oh, okay, good. Because I was getting a little bit annoying to deal with, having to breathe through my mouth. So with that being said, okay, yes, back to the points. 7 valence electrons here. So now for CHCl3, okay, we want to account for in total 7 times 3, so that's 21. Okay, 1 electron here and 4 here. So if we add it all together, it'd be 26 valence electrons. Okay, and for the CCl4, right, kind of the same thing, because now we know that chlorine has 7, so it'd be 7 times 4, that'd be 28 plus 4, so it needs to account for 32 electrons. So it's not actually electrons that determine polarity, but it helps us draw our Lewis dot diagram. So starting with CHCl3, we want to put the carbon in the middle, because carbon is typically in the middle. Okay, and we have Cl, 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 H. Okay, and then we fill out the chlorine specifically because of the fact that they have more valence, so they need to account for it, more valence electrons. And then we see if we accounted for the right amount. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oops, I think I miscounted. 2, 4, 6, 8, 10, 12, 14, okay, 16, 18, 20, 22, 24, 26. So this does have 26 valence electrons, and if we quickly did the math for the electron number, it would be 4 minus 0 plus 8 over 4, since there's 8 electrons being in a bond. That does equal 0. For the hydrogen is 1 minus 0 plus 2 over 2. Same thing, it's also equal to 0. And now for the chlorine, it's 7 minus 6, because there's 6 electrons in the valence, in the lone pairs, plus only sharing 1 bond, so 6 plus 2 over 2, that's 7, so 0 as well. So this is perfectly how it wants to be. Using that information, really, you can kind of just copy and paste this this to get the chlorine of what it would be. The CCl4, because instead of an H there, it's really just a chlorine here now, and then bam. And if you count the electrons, we would have the 26 like we had, plus 2 more, so 28, 30, 32. So this is also what we would want to be. So Now, why is this polar? I mean, why is this one non-polar here, the CCl4, and why is CHCl3 polar? Let's look at the electronegativity. Let's start with carbon and chlorine, actually. So chlorine and carbon, right? We have 3.16 for the electronegativity on chlorine, minus 2.55, okay? 0.61. Okay, so there is a, I guess, negative slight charge, okay, all out, okay, towards the chlorine, and the carbon is where like the positive charge is, right? But it's all equal because there's all chlorines in each I guess end. So this one would be kind of like a tetrahedral in terms of molecular geometry. Same with the other one as well. Well, point being is that these are all polar bonds. So if I actually were to redraw it, right, it'd be C, kind of like look like this, and this would be Cl, 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 Cl. But because they're all pulling the same direction, okay, it ends up being non-polar because everything, you know, is equally pulling. Now, with that being said, though, when you compare this one here, right, still the same shape, okay, alright, still the same shape. The difference is, though, that the hydrogen's electronegativity is a little, well, quite different actually. As I said, these are all polar bonds. So guys, this is still polar. Oops. This is still polar, polar, polar. Because the cutoff for polar, right, when I did that math, okay, it has to be anything greater than, if I remember correctly, 0.4. And 0.6, although it's not that much greater, it's still greater than 0.4. So it counts as a polar bond. So now let's compare carbon and hydrogen, though, okay? Carbon and hydrogen, 2.55 minus 2.20 for hydrogen electronegativity, 0.35. So this bond right here actually is non-polar, okay? Meaning that now you have a pull, okay? An uneven pull of all these three pulling, but hydrogen's not putting its work in. So because hydrogen is not putting that work in compared to everything else, that makes CHCl3 polar. But with CCl4, because everything is pulling the same amount, because they're all the same, I guess, electronegativity, which does arise from having the same elements in each corner. But you notice that some elements that are close enough in regards to electronegativity, you notice that there's like, although it's kind of polar, it could almost be argued that not really. But you'd barely find out on the periodic table as I'm going through right now. So like, because every element seems to have its own specific type of electronegativity. So exactly. So in terms of situations like that happening, I would say you can err on the side of least likely, because even something like nitrogen and bromine, which are actually quite close, still end up exerting just slightly enough different forces to where it will still be considered polar. So the point being here is that if it's different elements, you're most likely going to be dealing with a polar molecule. Even if it was CH2Cl2 like this, it would still be the same issue, because they would have, because remember it's a tetrahedral, right? So you'd have a hydrogen here, a chlorine here, and a chlorine there. Because if we're looking at a 3D structure, you would still have uneven pull on this side, so the hydrogen's not pulling any work in. So even this would still be polar. As soon as you have different elements involved in your like surrounding atom, then you can assume most likely it's going to be polar. So in summary, that's why CHCl3 is polar and CCl4 is non-polar, because of the fact that, you know, as for one, we've shown it through the whole actual I guess electronegativity, and two, exactly, we're dealing with different elements with the outer shell, outer surrounding atoms, then exactly that would be what you consider polar, because they're different. Okay, so let's see here. We have CHCl3. You can see clearly with the Lewis diagram is like the chlorine are quite different from the hydrogen, but more importantly, the electronegativity is different, and it's asymmetric, which results in there being a movement, causing the molecule to behave as a polar molecule. CCl4, you see how it's so nice and evened out and spread out? Exactly, is because it's 4 symmetrical CCl bonds. Now, with that being said though, okay, don't forget that these still count as polar bonds themselves, but because there's polar bonds going the exact way in each direction, overall it becomes non-polar. Now, don't be fooled by the Lewis dot diagram though. If I had, as the last example, CBr2Cl2, something like that, this is still going to be a polar molecule because of the electronegativity. Even though everything looks nice with the electrons all filled out, because bromine and chlorine have different electronegativity, that is why it's going to still be a polar molecule, because they're not pulling the same amount on each side. So with that, this is correct, and I hope with this you'll be able to understand polarity just a little bit better.